we all have an intuitive understanding of what the probability of a certain event means. Typically, we imagine an experiment, and that the probability of a certain outcome is the relative frequency of times the outcome is observed when the experiment is repeated independently. For instance, when tossing a coin or rolling a die, we can evaluate experimentally the probability of a certain outcome by repeating the experiment many times. We thus come to an objective conclusion of what the probability should be. When predicting tomorrow's weather, there is no experiment to repeat. The probability of rain will thus reflect our best guess based on current information. Although more subjective, we still typically think of this probability as some kind of average outcome that we may expect to see. The mathematical notion of probability is defined without reference to an experiment and relative frequency of outcomes. So, how can we be sure that the mathematical definition agrees with our informal and intuitive understanding of probabilities? In order to discuss this question further, let us first recall the mathematical definition. So a probability space is a triple consisting of a set omega, a collection F of subsets of omega, and a function P which to each set in F assigns a real number. This function should satisfy three properties of a measure. The set omega is referred to as the sample space. Elements of omega and F are referred to as outcomes and events, respectively, and P is referred to as a probability measure. We can use probability spaces to construct models for an actual experiment. For instance, a probability space describing the experiment of rolling a die can be constructed as follows. The sample space consists of all 6 different outcomes of the die, F consists of all subsets, and P could be the measure that assigns equal probability to the 6 outcomes. Of course, there's nothing that prevents us from assigning different probabilities to the outcomes. But that would not describe the roll of a fair die, but correspond simply to a different experiment. Our intuitive interpretation of probabilities as relative frequencies suggests that the probability of an event is a number between 0 and 1. Moreover, for disjoint events A and B, the probability that one of the two occurs equals the sum of the probabilities. This is in agreement with the mathematical definition. However, it is not immediate from the definition that when an experiment is repeated independently, or more precisely, that in a probabilistic model for an experiment that is repeated independently, the relative frequency of occurrences of an event does indeed correspond to the probability of that event. In order to discuss this further, we should first discuss what it means mathematically for 2 experiments to be carried out independently. 2 events, A and B, are independent if the probability that both occur equals the product of the probabilities. For an experiment where all outcomes occur with equal probability, for instance the roll of a die, the definition can be motivated using the multiplication principle. In this context, the probability of an event A is simply the ratio of the number of outcomes favorable to A divided by the total number of outcomes. if B is an event in an independent experiment, then it follows from the multiplication principle that the probability of both A and B occurring equals the number of outcomes favorable to both A and B divided by the number of pairs of outcomes. By the multiplication principle, this equals the number of outcomes favorable to A times the number of outcomes favorable to B divided by the number of outcomes squared, which is the product of the probabilities. The general definition is now an extension of this equiprobable setting. Let us now consider an experiment repeated independently. Let A be some set of possible outcomes of the experiment, and let xk be the indicator variable of the event A occurring in round k. Then xk is Bernoulli distributed random variable with parameter given by the probability of A occurring, and in particular we know its mean and variance. Since events related to different rounds of the experiment are assumed independent, the variables x1, x2 and so on are also independent. Let n subscript n be the sum of xk for the first values of k. By independence, we can compute again its mean and variance. N subscript n divided by little n corresponds to the relative frequency of occurrences of the event A when the experiment is repeated. Using Chebyshev's inequality, we may bound the probability that this relative frequency deviates from its expectation by a small number. For large values of n, this number is very small. This shows that with probability close to 1, the relative frequency of occurrences of the event A when an experiment is repeated independently a large number of times differs very little from the probability of that event. We may hence conclude that the mathematical notion of probability corresponds well with our intuitive understanding of probabilities as relative frequencies of occurrences.